I'm Simon Danisch. I work at Nexternal at the moment. I'm their Julia expert. I've been working with Julia for around 6 years in graphics, in GPU acceleration, and on the plotting infrastructure. Today I will talk about what Julia is and when to use it. I will talk quite a bit about how to call other libraries and a bit about the performance of Julia compared to other languages. I will talk a bit about how to write nice composable libraries in Julia and how it's unique in that regard. And I collected a few noteworthy examples to give you a taste of how Julia looks like. And I will finish with a little demo of how you can call Julia from Python and discuss a bit like the disadvantages of Julia. And this is all in Nexternal, the company I work at. So it's a notebook platform where you can run Julia and Python in the cloud. And it also has a presentation mode, which I will be using. Right. How does this work? Nope. Okay, so what is Julia? I usually describe it as Python at the speed of C with very elegant syntax for math, like from MATLAB. So you get all the dynamic features from Python and the interactivity at the speed of C, and I think it combines the advantages of these languages. It's also multi-purpose like Python and multi-paradigm language, so you can combine more functional approaches with more object-oriented approaches. It appeared in 2012, so it's pretty young compared to Python, but it's also already pretty usable and mature and steadily growing. Then my favorite feature list from Julia is that it inherited quite a bit of goodies from Lisp, like fully featured macros, that you can treat code as a data structure, so you can just manipulate it like any other data structure and eval it, and a lot of functional programming inheritance. One of the most noteworthy features is multiple dispatch in Julia, where you can compose multiple functions very nicely by not just dispatching on one argument, but dispatching on the type of multiple arguments in your function. I will talk a bit more about it later. And I really enjoy the optional type system in Julia because it doesn't get in your way if you're just writing something, but if you actually sit down and want to write a mature library, it's really nice to have a fully featured type system. And Julia has a lot of introspection and reflection functions, so you can look actually at what code Julia generates down to the assembly code. You can look where functions are defined. You can immediately get their source code and things like that, and get help for function, which makes it very easy to get started with Julia. I tried to make a little graph about when to use Julia and where it's used. So here on this axis, I have like the theoretically niceness of Julia's features in this area. And here I try to roughly estimate how many projects there are in Julia at this moment. And why I said theoretically nice, it's because the more projects there are in an area, the easier it will be to use and the less awkward. So if it's not theoretically, it would just be like a straight diagonal, because if there's only one person using Julia, for example, for a hard real time, there won't be many libraries for it and it will be awkward. And this is kind of the case for machine learning, I think, in Julia, because Julia has very incredible features for machine learning. Because it's fast, it has very good GPU integration, but not many people use it for machine learning at the moment, so there are definitely libraries missing. The strong part is more in scientific computing. Julia was created for this, and for optimization problems, Julia has a long history in optimizations with JMP, which was a very successful library early on. and it probably offers the state of the art for solving optimization problems. And there are a lot of physics and simulation projects with finite element simulations, and probably Julia gets its most money from big finance company doing finance modeling. And nowadays there are quite a few climate modeling projects in Julia. So in this area here, I can definitely say you should take a look at Julia if you work in this. If you go more into this area, I'm like, okay, Julia might be great for this, but there are not as many mature libraries yet. Some people use Julia in production with web servers, but yeah, you won't have all the libraries there, and some of them aren't very mature. The same is true for desktop applications. Not all of them are nicely wrapped yet. Qt, there's a wrapper, but it's not well maintained and things like that. But there are desktop applications, so it does work. Hard real-time is an interesting one because Julia is a garbage collected language, which usually doesn't work as well with a hard real-time. But since you can fairly easily write Julia code without doing any allocations, you can actually use it for hard real-time. But I think there's only one project that is actually doing that. So there's not much data about it, how nice it is actually in the end. And here, like in the bottom corner, that's something that doesn't really work in Julia. So if you're trying to target iOS, Julia doesn't run on iOS. I'm not sure when it will run on iOS. On Android, actually, like, I think 2 weeks ago, it started running on Android, but it's still in an early phase. So there's not much to say about it if it will be nice. And for really secure application where you probably want to prove that your program is bug-free and things like that, Julia isn't the right language. It's not battle-proofed in this, and yeah. Now, Julia is very famous for its performance. That's what it's known for. So that's definitely one of the biggest use cases. And you can see this nicely on the slide here. It's a few micro benchmarks compared to other languages. The baseline here is C. And you can see that Julia really nicely is around the C performance. And I think you can even go as far as that this like variance around it, that you would get a similar variance between different C compiler versions. So it's usually very close. And in all my years comparing C and Julia performance, it was usually a bug if Julia didn't reach the same performance. Now, why is performance important? I hear a lot. There have been a lot of articles about like, yeah, I don't care, Python is fast enough. Why should I think about this? And my main reason for this is that I want to set on a language where I know that I don't have any barrier in the future, because probably the moment where you run into a problem, you have like a lot of deadlines and you want to really finish your project, and suddenly you notice, shit, the performance doesn't work out. It's unusable. That's probably the worst moment where you want to switch languages. So I try to set on a language where this won't happen. It's relatively easy to write Python code that runs as fast as C because it actually calls out to a lot of underlying C libraries. That has been working out really well in Python, I think, and combines the best of the two worlds. But someone has to write those libraries, and those people probably also want to have a nice language to write in. And sometimes it's just really awkward to express your program in terms of calling out to a C library, because you need to use plain data types like arrays and numbers, and need to get rid of classes probably and all the nice things you started loving about Python. And now finally, when people consider switching to Julia, they will say, well, I have all these nice libraries, but Julia actually has very nice foreign function interfaces for most major languages. And one of the best developed one is actually PyCall, so for calling Python. And that's because historically the Julia and the Python community have been working a lot together. There's been a lot of people working together on this. So what can you do? By using PyCore, you can just import any installed Python package. You can define Julia callbacks and just feed them into a Python function. Here, this is just another syntax in Julia to have a short form of a callback. And this works just like passing a C function to Pythons. So it will have a similar performance. You can also even inherit from Python classes. So this is a Julia macro that gives you this kind of hybrid domain-specific language between Julia and Python to define a Python class that inherits from the polynomial from NumPy, and then you can just use it like a normal Julia type, but also pass it to any Python function that accepts a polynomial. And you can even write whole functions in with this kind of string macro here. This will immediately execute this in Python and define this PyMap. So that's just a very simple function. It maps this function f over the array b and writes it out to a, the result. And we can wrap this in Julia here and create this Julia function PyMap, which we then can compare to the Julia inbuild. So this is a funny little syntax here with the dot notation that you can apply any Julia function to any Julia array, and it will just, it's pretty much like a map, and it has a lot of nice properties, but I'm not going more deeply into this. Yeah. The same is true for calling C. So we have this little C snippet above there, which implements the same function. So it's also a map implementation. You can shell out to compile this little C function into a shared library. And the code to actually call the C function is a bit more complicated because it's a statically typed language. So you actually need to define with what types you call this function, and you need to define the argument types and the return types of the function you're calling. But then you can just call the C function just like any Julia function, and it will work without any overhead. And finally, there's also a C++ wrapper library called cxx.jl. It's a bit more complicated because C++ is much more complicated. So it actually also allows you via the string macro to define arbitrary C++ code, which is very handy if you want to wrap more complex C++ libraries with templates and classes. And then you can also call this C++ function with the cxx macro and call it just like any normal Julia function. Now let's talk a bit about performance. Since all those wrappers, like even the PyCore wrapper, shouldn't have any overhead, it will just convert the array to a NumPy array, I think, without any copies. The same is true for the C functions. So it's possible to benchmark those codes from inside Julia without any overhead. And I'm using benchmarks tools, which tries really hard to make statistically significant benchmarks. It's a bit awkward to call here, but that's how it looks. And now if we compare this, we see that Python takes 55 seconds for this simple map. C and C++ are around 1.1 seconds, and Julia is a bit faster than that, 2 times faster, I think. So in an extreme case, this is definitely an extreme case, Julia can be 600 times faster than Python for such simple things. Why is Julia faster than C++ and C? Obviously, you can get the same performance in C because it's very close to the hardware, so you can always get the top performance. But I think it's missing some SIMD optimization, which is a bit harder to get in C. And I didn't figure out the correct command line flags to get it, but if you play around it, you will get the same performance as Julia. Now, can we go faster than this? And the answer is yes. Julia has pretty nice threading integration. This add threads macro existed for quite a bit of time, and with Julia 1.3, which got released a few months ago, this threading infrastructure is way better nowadays, but also a bit more complicated, so I'm not going to talk about it today. But yeah, you can just make a loop threaded with this macro and be even 2 times faster than the fastest Julia before. And since Julia has a very nice GPU integration, you can even easily move things to the GPU and then call the already existing map function and be even faster after that. What I want to point out here is that this actually does compile Julia functions to the GPU. So it's not restricted to some arbitrary set in Q arrays, but you can write your own Julia functions and map them over an array, or write your own CUDA kernels in Julia while using all the nice abstractions from Julia, which is pretty unique. Now, that means utilizing all these tools in Julia, you can be up to 180 times faster than the C solution. Of course, that's not fair. Of course, you could go to C and also go through all these hoops and call out to the GPU, but I think what I want to point out here is that in Julia it's very easy, and you just have all these tools readily available. And the takeaway from this is Julia does offer state-of-the-art performance. It's relatively simple to get there, and it has great interop. There's also even Java call, R call, and you can call to MATLAB, which I haven't showed. And while offering all of this, it still stays interactive and fun. Now, in the last 2 years or so, there has been a new motto been forged in the Julia community. It's come for the performance, stay for the syntax, because a lot of people were actually like, yeah, I really need this performance of Julia, that's why I'm using it. And then they were writing more and more libraries, and they were more excited about the actual syntax features and how you compose code in Julia. And that it's actually nice to have a type system compared to just having everything untyped. And multiple dispatch has been come up as a very nice way to compose code and extend existing libraries. And I hope that this isn't too much code to simply point out what I'm talking about. So above here we define a module. That's how you can structure your Julia code in isolated modules. You can have abstract types in Julia, which are defined like that. Then you can have concrete types. I already made a more advanced concrete type with a type parameter. That means these fields can take on any type, but they need to be the same one here. And it inherits from an abstract caller. Now in Julia, instead of binding methods to the object, you actually just overload functions. So here you just overload the base tuple function to convert your RGB value to a tuple. And then you can also overload the plus operator here. And this syntax says overload this for the argument t for all t that are inheritant of abstract caller. And then we just convert it to a tuple, do the plus with the tuple, and create a new instance of the type t. And having this base package means we can very easily define a new type, like a new color space, for example, that inherits from abstract color. And all we need to do is define this tuple conversion, and we get the plus for free. So this just works out of the box, and that makes it very easy to combine packages, especially because you then can just put it into a sum function, which just expect your data type in the array to have plus defined for it. So this works out of the box. And what's also pretty outstanding in Julia is that it has the same performance as built-in types. So when you compare this to building the sum over 3 times as many floats, you will see it has almost the same performance as doing it with the more complex types that wraps 3 floats. And that means you can actually define your own number types if you want to track your accuracy in a simulation and things like that. Or dual types, complex types, they don't need to be built in Julia to actually be fast. Now, some catchy examples I selected from data science. This is the state-of-the-art CSV parser, which is by now in performance on par with the fastest CSV parsers there are. Data frames is obviously the data frame library in Julia, and there's plots, which is the go-to plotting packages. And statplots is actually just an extension of plots, and it's very similar to this color extension thing I showed you. So it's just extending plots by a few more functions and this kind of domain-specific syntax to more concisely make statistical plots. You can have a look at it. I won't go through this. I will also publish the slides, so you can probably look at it in more detail. Compared to it, there's also query.jl and quite a few other data transforming packages. This one uses Julia's macros to define a domain-specific language to have a more concise way of defining data transformation, and it's tightly integrated with Vega Lite for plotting, so that works very well together. I think everyone just needs to find out which style they prefer more, and there are quite a few Julia libraries for that. Julia also has a neural network library, which is called Flux. Its features compare roughly to what TensorFlow offers. Mostly it's as fast, but because there are fewer people working on it, there are definitely some performance bugs. It uses the Julia GPU acceleration infrastructure, which allows the framework to be 100% written in Julia while still having GPU acceleration. And last time I checked, the implementation was around 2,000 lines of code. So it's really approachable. You can actually go in there and look at the code and understand what's going on, which is very nice if you need to debug something. And it also works with plain Julia arrays, types, and functions, because usually you can't do that because you need some GPU acceleration, but because Julia can actually compile those functions for the GPU and also has some pretty good automatic differentiation for custom functions, you can use those in your layers. This is how it looks like, just to give you a taste. There are many more examples like this in the Flux Model Zoo if you're interested in this library. And yeah, I think it's a very promising library because I don't know if you know the TensorFlow and Swift project, but it's very similar to that because it's actually using compiler plugins instead of writing a new compiler around it to get good performance. And that's where we come to hook into the compiler, because Julia actually allows you to hook in very easily into the compiler. And one of the main packages that make it possible is this cassette library. How it works is that you define a new context in which you execute functions, and in this context you can completely rewrite anything that gets called and any function that gets called in this context. So for a simple thing, there's this pre-hook function that gets executed before any call, and I'm just using it to print what I'm calling next. And if I then multiply, for example, execute a multiply in this context, I will see the whole call stack for this. And if you're saying, now, wow, that's a lot of function calls for a simple multiply, that's true because there's a whole promotion engine and things like that, but this actually gets compiled down to be as fast as C, because all of these are free abstractions in the compiler. What you can also do is you can actually change the implementation of a function. Here I'm just doing something really silly. I just override the convert function and multiply it by 3, which completely changes our result. But this is very powerful and can be used for implementing automatic differentiation and things like that. Or also there's a package that uses this to rewrite loops to execute them on the GPU and things like that. And this all just works based on the Julia just-in-time compiler and is as fast as if you would execute it directly, the resulting code. I also wrote an interactive library. It's super early. This is probably the first time I'm showing it. I'm hoping it's still running. It's not. The problem is NextJournal shuts down the runner after 20 minutes, and I guess it has been 20 minutes. This needs to communicate with the Julia process in order to update the values. But how it works is you can just use the markdown syntax pretty much, and you can interpolate sliders and values into it, and they will just update accordingly. So this should update the plot in here. Yes, much like PyWidget. It's very similar. It also runs in Jupyter, it also runs in the Atom IDE, and you can also just serve it as a web page. All right, I guess this is probably going through some people's mind right now. So yeah, it's really hard to leave a language if you already, all your colleagues work in it. You have a lot of libraries you really like, but if you're really serious about Julia and want to offer your colleagues to still work with your packages that you write in Julia, it's possible. There's good news and bad news. That it's possible is the good news. The bad news is that it's not that used at the moment. So I had quite a few problems getting this to run, but in the end it was running. So there's the Julia package in Python. You can just start importing any Julia package, much like the PyCall example before, but the other way around. Then I wrote a bit of wrapper code just to make it a bit nicer to use. And then you can just call, this is my plotting library, you can just call it from Python with NumPy arrays and with keyword arguments and everything. It works. Now, what's bad? You probably already see here 88 seconds execution time, which is really bad for a language that I just sold you as to be super fast. This is all compilation time. And yeah, that's really bad. But you can compile it ahead of time, but it still doesn't work completely. It's a bit of a hassle, so people just do it if they're really forced to, if they want to deploy it or things like that. And actually, it's not such a big problem for most Julia developers, because if you develop locally, you will just start Julia one time, load all your packages, and from there on you will only compile diffs. So any new function you define, and that will be instantly. So after everything compiled, you will have pretty much the same latency as in Python. But it can get annoying, especially if you try to compute something in the cloud where it's expensive to just waste computations and things like that. But yeah, deploy is also bad. It's related because usually you want to compile things ahead of time if you deploy it. But it's a work in progress, so some people are already deploying Julia to different platforms, but they had to do it with a lot of manual work to get it running. And I'm actually working on a package to improve this, but it's a slow progress because I don't have that much time. Other people are working on it. But it's happening. And that brings me to my last point. When should I use Julia? I think library authors that need high performance and complex mathematical code, I think I can say you can immediately start using Julia, because it's really fun to write libraries in it, especially if they're from scratch and not super large with a lot of compilation times. And if you want smooth deploy and smooth ahead of time compilation, I think that's probably ready in 1 to 2 years. And the compiler team is working a lot on having a half interpreted mode and half compiled mode. So then you will get the best of Python and Julia in one language. But that will take some time. And I think in 3 to 5 years, you can probably expect that most problems in the ecosystem are fixed. Probably some ecosystems will still not be as nice as in Python because nobody invested time in it. But I think in the really serious areas, we will have it in 1 to 2 years. All right, thank you. Maybe I should... I don't have a session share. Any questions? Yeah.
I can also do your Q&A for the rest.
Thanks.
Now, okay, is this on?
It was this one.
Okay, good. When I started learning Python, I didn't know about PEP 8, so I wrote a lot of code that didn't look nice. When you begin in Julia, is there anything about code style you should know when you begin?
If there's anything about code style, yeah, I think there's some no-goes. Some people come from other object-oriented languages and write to the forum, how can I write object-oriented in Julia? And everyone is just like, no, don't do this. We have something better. And there are some style guides out there. They're a bit ignored, I think. But the official documentation has some comments about what you should avoid and what you should be doing, like when you should type your signatures of your functions and things like that.
Other questions?
Hey, from your presentation, as far as I understood, you can directly inherit from classes in Python.
Mm-hmm.
Is that correct? And can you a little bit elaborate so how that works? Do you get all that you have in Python, like everything predefined, upper the hierarchy in Julia, and how you call that, like just for wrapping my brains around that?
Yeah, so I think how it works is that this macro actually generates Python code to define a Python class, and whatever function you passed in there or defined in there will get passed to the Python class as a Julia function that then gets called as a method inside that class. So it's very similar to passing a callback function, and then you just have a thin Julia wrapper around that Python class on the Julia side.
But it takes like Python engine, and it goes through regular Python distribution that you have, so you need to have both, or like how's that getting together?
I need both of what?
So it's just taking Python code, and do you need the Python distribution itself? So does it go through Python engine to?
Yes, you need to have a Python installation.
Mm-hmm. Okay, thanks.
Any other questions? Okay, thanks for the talk. Oh, well, sorry, there's another question.
Thanks. So one thing I really like about Python is that the code is very readable. Mm-hmm. And just judging from the examples that you showed, it didn't look as readable, I'd say, to me. So would you say that, so in the beginning, is it hard to grasp the syntax? So is there like a steep learning curve?
I guess it depends on where you come from.
Python.
Yeah. I haven't been coming from Python, so I can't completely judge it. I just know that there are a lot of math examples where the math looks much nicer in Julia. Of course, if you're really set on object-oriented programming, it will usually take some time to grasp how to write things in Julia. Yeah, I think usually the syntax is as nice and comparable as Python. There are a few things like people don't like the and in Julia, but I think that's nitpicking. If you write an and or if you leave it open. We write and don't have any like tab problems in Julia, so I don't know. I think these are minor things, but there are definitely some examples. I should have linked them all. I will probably update the slides where you can really see how much nicer you can sometimes express a problem in Julia. Of course, they're probably the other way around sometimes, but yeah.
Okay, well, thanks for your talk.
All right, thank you.